This is Tom Sargent, and I'm going to give a couple of lectures in our class. So today I'm going to begin with some background and give you some perspective on things YARDA has been doing and things you've been reading about and how it fits together by merging theory and econometrics, and both merging and distinguishing the roles that these two play. So we're going to back up and be a little abstract at first, and then we'll dive into particular things. And the purpose of this lecture is to be a bridge between the theory and econometrics, and be sort of a guide to what you're going to be doing all year in several courses. So here's the idea: we're gonna use some language. Theory and econometrics have intimately related problems in mathematics, and the right way to view them is two sides of the same coin. So what scientists call theory is they say it leads to a direct problem, and they talk about econometrics or inference as being the inverse problem. And in play in both of these are exactly the same object. And the key object is going to be I'm going to write a probability distribution or a probability density, and I'm going to commit some notational sins. I'm going to use F for a generic density, and the reason I say it's a sin is it's going to denote different functions at different times in terms of the context. So there's going to be a density, and there's going to be two kinds of objects. There's going to be data, and those are going to be Y, and there's going to be parameters. And life is such that there always have to be parameters. And there's going to be a density. We're going to take the view that both of these are going to be random objects, and they're going to appear. And theta is going to, this is an annoying detail that has significant ramifications down the line. This theta is going to have to belong to some set big theta, and that's going to have to be a compact set. And the restrictions on theta are a subject of an advanced topic in econometrics that I'm not going to touch on, but just to warn you. Okay, so here's going to be the notation. I'm going to let Y with a vector sign above it right here. That's going to be a sequence of vectors dated by time. Since this is a macro class, most of it's going to be time. Although when we do cross-section work, there might be indices for individuals too. But I'm going to let this be YT is an n by 1 vector, and Y with the vector in front of it is going to be an infinite sequence. This is an infinite sequence. So it's a sequence of vectors. And then I'm going to let this Y0t be a partial history going from 0 to t. Okay? So those are going to be the these are going to be the observations. That's what the Y are. Okay, and we're going to call Y is said to be a stochastic process. What all that is it's a sequence of random vectors. the random vectors. And the key object that's going to be in play is we're going to talk about a joint probability distribution over a sequence or a partial sequence. So in particular, we're going to call this joint probability distribution F, and it's a joint density over this partial history for all finite t. And theta, we're going to index this distribution by a parameter. So we're going to have a probability distribution over a sequence indexed by a parameter that belongs to some set. That's going to be the key object that's going to be in play. Actually, it's been in play all quarter with YARDA, and it's going to be in play all the rest of your life in economics. So I'm going to use the following language. I didn't make up this language. So I'm going to call a model is a probability distribution over a sequence indexed by some parameters. Otherwise, you could shorthand, you say a model is a stochastic process indexed by some parameters. My friend Lars Hansen calls this a quote-unquote statistical model. Okay, so when I say model, that's what I mean. Okay, so what's the job of theory? The job of theory is to build a model. And Yard has done that. He spent some time with a first-class model, really important model in economics, the McCall search model. That fit the definition? Yep. You should think about what the possible observables are, what the parameters are, what kind of joint probability density it kicks out. He's been talking about the tools for building models, particular tools that we're going to come back to when he's been talking about Chapter 2 material. Okay, so there's two classic problems. And these are problems that occur in any applied science. It's going to be called a direct problem. So here's a direct problem. Given a model, okay, I've written it out. It's a joint probability distribution over a sequence or partial sequence indexed by some parameters. And given particular parameter, theta, so that means we're given a particular, once we pin down this parameter, we're given a particular probability distribution over y, the partial history. The direct problem is to draw repeated samples from or somehow characterize the probability distribution of outcomes. That's called the direct problem. For many of the models that we write down, the McCall search model might be one. Doing that is often easier said than done. So there's a whole field of computational economics. There's classic books by Kenneth Judd, and Miranda and Fackler. And there's actually a website called QuantEcon, where there's a bunch of Python programs and Julia programs that are all you could think of. Almost every lecture on that site is directed to solving a direct problem. So all the ingredients that Yard has been teaching you and will be teaching you, and Lars and I'll be teaching you, are ingredients on how do we create and characterize this joint density of the observations. So what here a model is it's a machine. You're taking a theory um, and generating a joint density of possible outcomes. And here, so we should think parameters. Take a little digression. For an economist, the kinds of models that you're going to be building throughout your career, parameters are going to include things like they're going to be parameters of preferences, things like utility functions and discount factors, technologies, information processes, maybe some parameters indexing how much competition there is. So theta are going to be things that are going to tell you about the structure of the economy. And when you do this constructing of this, solving this direct problem, you're deducing the restrictions that economic theory puts on this joint density. That's what theory is all about. I'm going to come back to that with some little examples later. Okay, so that's what you're doing, and that's what theory does. That's what theorists do. Okay, or that's what we do when we're theorists, because macroeconomists have to be both theorists and econometricians. Okay, so now let's get the inverse problem. So the inverse problem is this. And notice the following. Notice that, well, okay, well, I'll come back to this. What the inverse problem is given a model, what's a model? It's a probability distribution over a sequence, a partial sequence, indexed by some parameters. So given a model, notice the following. We started here exactly the same phrases. So the same object's in play, and the same object is in the focus of our attention. So now when this given a model here, it's assumed that it's already constructed, so the theorist has done his or her work. Okay, and now let's read on. And now these things differ. And given a sample path, y0t, so I put a twiddle on there to say that's a sample path. And in life, Yarda might talk about this, we only observe one sample path. When we solve the direct problem, we use a computer to generate many sample paths, and we draw repeated samples from that distribution. Here, we're saying we have only one sample path in the inverse problem. So notice that difference. So given a model and given a sample path, the inverse problem is to make inferences about or estimate the parameter theta. So the phrase estimate or make inferences about, that's a little vague. We'll fill that in. Okay, so that's the inverse problem. So the direct problem is to take the theta as given and generate a probability distribution. The inverse problem is to take the data as given and say something about theta. Okay, now so there's another name for this object, F, this joint density, evaluated at a particular sample path. It's called a likelihood function. So what a likelihood function is, it's a joint probability density evaluated at a particular realization of the sample path. And given the sample path, it's going to be a function of the unknown parameter, vector, theta. So you'll notice when we stare at this, when I look at the vector problem, I pretend like the parameter is known. I pretend like that. And then I plug in, I use this joint density to tell me things about the probabilities of different sample paths. When I solve the inverse problem, I'm pretending like the data are known because I've observed them, and I want to say something about what that implies about theta. So there's two theories of inference, and they're different theories, and they're actually intimately connected for a reason I'm going to tell you about, because they involve the same key object, the same key objects at the core of both of them. So one is called, I'll give you a couple cuts at this. One is called maximum likelihood estimation of the parameter theta. And what's the idea there? It's to take, I should have put a twiddle here. It's to take the given data and find the theta that maximizes the probability that particular sequence of observations occurred. So it's to find the theta that according to the model made those observations the most likely. So you could ask yourself, why is this a good idea? Or in what sense is this a good estimator? I'll come back and I'll tell you an answer. That's one way. The other is Bayesian. So what the Bayesian approach is it's based on treating y0, this partial history, and theta symmetrically. That's the key idea. So what a Bayesian does is he views the observations as random given the thetas, but then he thinks that he doesn't know the thetas, and he treats them as random. He or she summarizes his ignorance about the theta in the form of a probability distribution. And this is a big step, he treats it as a probability distribution that produces a joint probability distribution over the object. You just use that as a big joint probability distribution. And that joint probability distribution, you just can use this. This is going to be a key equation. When I say he treats it symmetrically, he thinks, well, Fy0t and theta are both random. And he expresses that as saying, well, given theta, and then he has a probability distribution over theta. You can always do that. That's just laws of probability. And this is the likelihood function. And I'm going to put proportional here. No, I don't have to do that. That's the likelihood function. Forget what I just said. That's the likelihood function, and that's the prior. That's the name of this. So he's going to view that, and then what he's going to do is he's just going to write this joint density function in another way. He could factor this in another way. This is also equal to f of theta given y0t times f of y0t, the marginal density. Both of those can be written. It's just the laws of probability. So the key object is he's going to view this is a joint density over the observations and the unknown parameters. And then he's going to use Bayes' law. The star thing is Bayes' law. He's going to say, he's just going to use the mathematics of this to say, given this prior, he can, and given the likelihood function, he can just use this mathematics to deduce this thing called a posterior. It tells him or her probability distribution of the of the parameter that he's uncertain about, conditional on the observations that he's seeing. And if you stare at this, that's just Bayes' law. Okay. And this is an interesting expression here. I've written down, I'm just using simple probability. The so-called marginal distribution of the y's, look at this formula. It's the likelihood function, it's conditional distribution of the partial history given theta times the prior, integrated the whole thing over the parameters that I don't know. And this leads to what I think, that's the marginal distribution that my theory kicks out. Okay. So there's two theories of inference, and people have written books about this, about how friendships have divided. I've seen in my lifetime friendships divided, whether you're a frequentist or a Bayesian. And I'm just going to tell you here mechanically what frequentists do, and what Bayesians do. So here's what a frequentist does. A frequentist pretends what you do is you pretend that you know theta. You just pretend that you know theta. So this is not going to ask how you got that knowledge. It's just going to start from pretending you know theta. This is the so-called Neyman-Pearson paradigm. You're going to pretend that you know theta, and then what you're going to deduce from the theory is the joint density. Your theory gives you the conditional density of y0, the partial history given theta. And from that, knowing that distribution, you can get the distribution of anything that's called a statistic. So what's a statistic? Mathematician defines a statistician as a function of the observations. This is a statistic. So I'm going to call that statistic is just G. Notice it does not depend, I haven't written it as a function of the parameters. It implicitly depends on the parameters. Because the probability distribution of if I took repeated samples, then I'd get different histories, and I'd get different values of the G. So what a statistician does is he pretends that he knows theta, and then for that theta, derive the distribution, the implied distribution of the statistic G. That's it. Derive that distribution. And that's it. And then you ask, you use that distribution to ask various kinds of quote unquote hypothesis testing questions. In particular, if the parameter value was what I pretended it is, how likely was it that I got the statistic that I actually computed in the sample? That's the logical structure of that. Okay, Bayesians do something else. So the key thing is frequentists always start by pretending that they know the theta. That's not what Bayesians do. Bayesians start with a prior distribution. They confess that they don't know theta. And they're very proud of confessing that. They pretend that they don't pretend that they know theta. They never do that. Instead, they describe their ignorance with a prior probability distribution f of theta. And then they compute the posterior, given whatever data. And then the whole enterprise of Bayesian statistics. And you're going to you're going to meet, you're lucky because you have some great econometrics teachers this year, and they have strong views on this. Cogley and Christensen, I won't tell you what their views are. They have strong views on this. They do different things. Maybe one of them is a very religious Bayesian, and tears come to his eyes when you mention Reverend Bayes, and he actually once a year he goes to the place where Bayes was born and looks at a plaque. Okay, that's one of them. And then the other one is not quite that convinced. Well, you'll see when you get. Anyway, here's what a Bayesian does. First thing they do is that they describe their posterior. They say after we've observed the data, the posterior probability distribution tells us how uncertain we are about the parameter. And then great Bayesian said, well, so why should that be interesting? Well, it's very interesting if your prior is my prior. But what if we have different priors? If we have different priors, we'll have different posteriors. So one part of the Bayesian work says what they try to do is characterize the mapping from priors to posteriors, so that it's kind of user-friendly, so that you could kind of think of a toolkit. Okay. So there's a great book 40-year-old book by Edward Leamer, who talks about this. It's called Specification Searches. Okay, that's what Bayesians do. And what you'll notice is the important fact is the likelihood function, that is the model, is the key to both of these. It's both frequentist and Bayesian inference depend intimately on the likelihood function and the model. So it's the key to the direct problem, obviously, and it's the key to all approaches to the inverse problem. Every approach to the inverse problem is going to involve the likelihood function in a really critical way. Okay. So what I've done so far is I've given you a way to think about. Actually, you can think of it as giving you kind of like an organizational scheme for your studies, or you could think of it as an organizer for your desk. Like every class you go into, every seminar you could go into, you should be able to put what's being talked about or what you're learning about in one of these categories I told you about. You're creating a model. Is the guy using a model in a sense that we've used it? If not, he or she's not telling you everything that they're doing. When they're doing estimation, you could ask where it fits and so on. Okay, so this is a scheme that I think all good theorists and econometricians would agree on. But now here's the obstacle. The central object, what I'm calling the model or the likelihood function, it can be challenging to construct and to compute. The joint density over many variables. And people have gotten famous for constructing practical approaches to computing this joint density as a theoretical object or as something to be used econometrically. And many things that you'll study here, like Abreu, Pearson, Sticchetti got very famous for simplifying and making practical, calculating something that was a theory, exactly the sense I'm talking about, that people thought was very forbidding. And they made it, they wrote this couple abstract theory papers which vastly simplified things and opened up the way to a whole bunch of applications. Okay, but it can be difficult to compute. So it's a joint density over many variables. So now we're going to creep up on what Yard has been talking about. What's the remedy? And one remedy is to pray, hope, want. We're going to pray that YT is Markov. And what I'm going to show you, what I want to show you is why that prayer is. Okay, that's a prayer a number of people have made with profit, because the spirit is ask and it shall be given. But here you have to be very subtle about the way you ask sometimes. And that's going to be the theme of what we're going to talk about right away. Okay, to save paper, or my pencil, I'm going to suppress the theta now. So I'm going to write f without the theta, and the theta is there in the background. I want you to understand, and I'm just being lazy. So the understanding that we fixed a theta, of pretending that I fixed the theta, and so everything I'm doing is dependent on theta, and we're gonna see that later in this lecture. Okay, we're going to fix theta, and then what we're going to do is we're going to use the laws of probability to factor this joint density over this partial sequence. And here's the way it's going to go. We're going to write the joint density. We're just going to factor it like this. Now this is the key equation. So you can always do this. There's no assumption about Markov or anything else. So I'm going to write f of yt conditioned on the history between yt minus 1 and y0. I can do that. And then I'm going to write, and then I'm just going to write f of yt minus 1. I'm going to write that joint density. That's what I'm going to do. But that can be factored again. That's, go all the way, that's f of yt minus 1 conditioned on the history yt minus 2 all the way back to 0. But do it again and keep doing it, and you'll actually end up getting back to f of y1 given y0, that's all that's left, times the initial, the density of the initial y0. This is just the laws of probability, conditional probability. I'm just repeatedly applying them. And what I've done is I've factored, you could say I've factored the likelihood function, the joint density, into a bunch of conditional densities. And what I'm using is I'm just over and over again factoring. So is this the only way I factored things? I could have factored things? No, it's not the only way I could factor things, but I'll come back to that. But this is a very useful way to factor it. That's a starting point. And now we notice the following thing. Well, if yt is Markov, then that simplifies, and so on. And what if yt is Markov, then this looks like this. F of yt given yt minus 1, f of yt minus 1 given yt minus 2. And these are just the product of all the one-step conditional densities. Just the product. So all of these things look alike. The only thing that looks different is the initial condition. There's a probability distribution over the initial condition. So that's important. Okay. So a thing to notice is that this, if this is true, it's if yt is Markov, then computing the joint probability distribution over a sequence can be reduced to computing the product of a bunch of conditional densities and then multiplying them by a probability of the initial condition. Now that turns out to be a huge saving if you can do it. And Okay, now what you'll notice is what Yarda has done in chapter 2, much of the time, not all the time, much of the time, is he's assumed that yt is Markov, or xt was Markov. So here's an example. Suppose and here's an example that you've seen. Suppose yt looks like this. Yt plus 1 is ayt, that's a vector, plus c times epsilon t plus 1, where epsilon t plus 1 is normal 0 of the identity matrix. And this is true for t greater than or equal to 0. And then I'm going to assume that y0 is normal with mean mu 0 and covariance matrix sigma 0. You've seen this before. Or another way to do that, so go to Wikipedia and look up the definition of a multivariate normal distribution. You'll find that the log of the probability distribution of y0 is this. It's minus 1/2 n log 2 pi, where n is the dimension of y, minus 0.5 log det, log determinant of the sigma 0, minus 1/2 y0 minus u0 prime sigma 0 inverse that standard formula. And then what's true is that log the conditional distribution, the log of the conditional distribution is really easy to compute. It's just another log normal. And now the conditional mean is AYT. The conditional covariance matrix is CC prime. So now we've computed this. So we can compute the log of F of Y0T. That's just going to be the sum of a bunch of terms that look like, it's going to look like, we can, let's see if we can do it without, okay, I'm just going to add these up. I get, I'm going to get t plus 1 of these terms. You get t plus 1 of these terms. And I'm going to get a sum. I'm going to get a constant. We could figure that out. Minus 1/2 summation. And I'm going to go tau equals something to t. And I'm going to get y. Tau plus 1 minus a y tau prime c prime inverse y tau plus 1 minus a y tau. I just sum that where tau goes from 0 to t minus 1. And then I have to add in plus log f0, f of y0. So the point is it's very easy to write, which I've given you a formula for. It's very easy to write down the log of the log of the joint density just by summing up the log of the conditional densities and then adding in the log of the density of the initial condition. Okay. Okay. So, and there are some models. There are some models in which that we could write down which turns out A, C, what are the free parameters? Mu 0 and sigma 0 are all functions of just a parameter vector theta belonging to theta. So if we have a model that looks like this, then we have a very easy algorithm for solving both the direct problem and the inverse problem. Because you give me a theta, I'll give you an A, C, mu 0, sigma 0. I'll plug them into these formulas, and I can simulate to my heart's content just by drawing normal random variables. Or I can solve the inverse problem by doing some version of maximum likelihood or Bayesian method. This is really all very good, but now we're going to set up the next part of what we'll be talking about. But suppose instead our structure is this. Something's Markov. But what we see, the yt's, are functions of something that's Markov. And I'm going to write this down. I'm going to write Vt is normal 0 with some covariance matrix R. And I'm going to write down, I'll write down exactly what I did before. X0 is normal. Start the thing off with a mu0, sigma 0. Okay, what this is there's something that's Markov. Xt is Markov. Yt is not Markov. It's not Markov for a couple reasons. G, so the idea is what we observe is a linear combination of something that's Markov plus some VTs, and that could be measurement error or it could be real stuff, not measurement, accurate measure, but it's additional source of noise of random variation that impinges on the y's. You can check out y is not Markov, x is, but we see y0t, we never see xt. So this is called a hidden Markov model. And if you do Google on hidden Markov models, they are used all over the place. They're used in image processing, language translation, just all sorts of things. They're used just all over. So this is the simple, classical linear Gaussian hidden Markov model. And so the question is, what do we do? And is there some way, so wouldn't it be great if we could do something like this? But we can't directly because y is Markov. So where we're going to start off after the break is we're going to see if there's something we can do.